because it's which is on biorefinery, fan print, surface modification by printing process, and I am in this team, MatBio, multi-scale bio-based materials. So you can see here the research which is performed in this team. So I will not develop everything, but it's mainly on the study of building blocks from vegetable biomass, suspension and blends, material process engineering, and composites and fiber-based materials. So I'm more in this area. So regarding my presentation today, there are three main topics. So first, I will briefly introduce polysaccharide, but you probably already know. The preparation of nanomaterials from this polysaccharide and the difference that results from the change in the scale of the material from the micro scale to the nano scale. And of course, it results in new applications. So you know cellulose, so you know the chemical structure of cellulose, which is here. Cellulose acts as a structural materials, mainly in plants, but also some animals, and it is also obtained from some bacteria. So it's the most abundant polymer on Earth. You can see the annual production here. And on average, a tree produces about 10 grams of cellulose every day. So it means that we have an abundant resource, and only few percent of this resource is used, for example, for the pulp and paper industry. So chitin is another polysaccharide, which chemical structure which is similar, but of course it's different. It also acts as a structural element, so it provides the mechanical properties for the cell walls of fungi, exoskeleton of arthropod, and insect. So it's the second most abundant polysaccharide in nature. And starch, we talk also about starch, which is another polysaccharide that can be found mainly in tubers and cereals. Starch is composed mainly of two macromolecules, amylose and amylopectin, which are very similar, except that amylose is mainly linear and amylopectin is a branch macromolecule. The function of starch in nature is different. So it's not a structural element, and you will see that it's important for nanomaterials. It acts as an energy storage material. So these three polysaccharides have common features. They are semi-crystalline and they exhibit also a multi-scale nanostructure. For example, in the case of cellulose, so in nature, cellulose is usually found associated with other materials. So cellulose is a structural element. It is surrounded by lignin, which is a non-polar polymer to protect, in fact, cellulose. And hemicellulose acts as a compatibilizer between polar cellulose and non-polar lignin. It's possible to extract cellulose from this composite, from these natural fibers, by different treatment. And the resulting materials, the cellulosic fibers, consist of aligned and strongly linked cellulose nanofibrils or microfibrils that consist of alternating crystalline and non-crystalline materials. So this is another representation of the hierarchical structure of cellulose in nature. So we can see this material at the level of 1 meter. This is a tree. And we can progressively decrease the scale of observation up to the cellulose material, the cellulose macromolecule. And we have here a nanoscale that would be interesting to prepare nanomaterials. So it's the same thing for chitin. So this material is also found in the form of microfibrils because it acts as a structural element. And this material, or these microfibrils, are embedded in a matrix that mainly consists of proteins. So starch is found in nature in the form of a powder. So it's flour, in fact, with more or less granular structure, with dimensions that range from 1 to about 100 micron, depending on the source of starch. And when looking to starch, we can see this onion-like structure that consists of alternating crystalline and amorphous domains. And again, this material displays a hierarchical structure up to the level of the macromolecule. So preparation of nanomaterials from these polysaccharides. There are mainly two strategies to prepare nanomaterials from cellulose, for example. The first one is based on a mechanical treatment. The suspension of cellulose fiber after purification of natural fiber is submitted to a strong shear action in order to progressively release the microfibrils from the cellulosic fibers. So different equipments can be used, which are here. So I will not describe all this equipment, but the effect is the same. So consists in applying strong shear force to the pulp, to the fiber pulps, which is pushed here. So it's a dilute suspension, usually around 2%. And this suspension is forced to pass into this very thin slit, which thickness change because of the movement of this valve. And so it applies very strong shear to the suspension. And after several passes, we can obtain a partial, at least, defibrillation of the material. This is the aspect of the material which is obtained after this mechanical treatment. Here we have 2% water, cellulose, sorry, meaning that we have 98% water. You can see that it looks like a gel, and this gel is stable in water, and this is due to residual hemicellulose. The yield is high, so it's almost 1%, and this gel displays a shear sealing behavior, meaning that when increasing the shear rate, which is applied to the suspension, the viscosity of the material decreases. So this is well known. So the preparation of this kind of material was first reported in 1983, but so it was only a lab curiosity because the energy demand to obtain this gel was very high. So it means that it's necessary to apply a pre-treatment in order to decrease this energy demand, and in this case, the application is possible. So different pre-treatment have been proposed, like for example, enzymatic hydrolysis, carboxymethylation, tempo-catalyzed oxidation, just to facilitate the separation of the microfibril. So you can see the aspect of this suspension here. So it consists in very long, flexible filaments that consist of alternating crystalline and non-crystalline domains. And regarding the dimension of these nanofibers, so the widths range between 2 to 100 nanometers, so it is in the nanoscale range. It depends mainly on the source of cellulose and also on the treatment which is applied to the pulp. For the length, you can see that it's very difficult, but these filaments are very long. So the degree of fibrillation can be performed using a different observation. So the turbidity of the suspension, it becomes more transparent because of the decrease of the size of the suspended object. The viscosity of the suspension increases. We'll talk about this later. The water retention increases. Well, it's possible, of course, to prepare films from this suspension just by evaporating water, and in this case the porosity of the film decreases and the density, of course, increases. These films have high mechanical strength. The degree of polymerization of cellulose decreases because of the strong shear action which is applied to the material. The specific surface area increases, and the degree of crystallinity of cellulose increases. So there is another strategy, which is a chemical strategy, let's say, that consists in an acid hydrolysis of cellulose. So remember that this microfibril consists of alternating crystalline and non-crystalline domains, and it's possible by using strong acid to selectively dissolve the amorphous or non-crystalline domains. So different acids can be used. Usually sulfuric acid is used, so the only difference with other acid is the surface chemistry of cellulose after this treatment. In the case of sulfuric acid, sulfate groups are created on the surface of the nanoparticles, and it helps to have a stable suspension in water. So you can see here the different steps of the treatment, starting from natural fiber. So of course, the first one consists in purifying cellulose, which is then submitted to this hydrolysis treatment. And so this hydrolysis treatment remove the amorphous domains, and then after purification, a sonication treatment is applied, mechanical treatment, in order to separate the nanocrystals. So the characteristic of these cellulose nanocrystals depend on the hydrolysis conditions, of course, but also on the source of cellulose. The yield range between 20 to 80%, so it mainly depends on the crystallinity of the starting material. The diameter is between 5 to 30 nanometer, and the length range from 100 to nanometer to 1 micro. You can see the aspect of these nanocrystals. Here they were extracted from rami fibers, and you can see that they consist of straight nanorods or rod-like nanoparticles with a high aspect ratio. So you can see here the evolution of the length of these nanocrystals as a function of the duration of the hydrolysis treatment. And so it decreases and then it level off when all the amorphous domains have been degraded or dissolved. So similar treatments can be applied to chitin. You have some examples here of chitin nanofibrils obtained by a mechanical treatment. So from a black tiger prawn, in this case. And so we have the same object, very long filaments. And also acid hydrolysis can be applied to chitin in order to obtain chitin nanocrystals. You have some examples here of nanocrystals extracted from squid pen, from crab shell, shrimp shells, and from Riftia tubes. So Riftia tubes is a quite, let's say, specific species of chitin. So it is obtained from this tube that contain a worm. So the worm can be between 1 to 2 meters long, and they are collected in the deep sea, 3,000 meters deep. And at this level, of course, the pressure is very high, meaning that the crystallinity of chitin is very high. And you can see that we obtain very long nanocrystals. So the average length is around 2.2 micron, and the diameter is 18 nanometers. So starch, can be also submitted to an acid hydrolysis treatment. So in the similar condition, except that in this case, the hydrolysis treatment needs to be performed at lower temperature. It is just because starch is more sensitive to acid hydrolysis. And so it means that, of course, because the temperature is lower, the duration of the treatment is longer. But during this treatment, we can selectively also dissolve the amorphous domain from the starch granules, and you can see the evolution of the aspect of the dispersion during the acid hydrolysis treatment. So you have here in white the crystalline domain. So during the acid hydrolysis treatment, these nanocrystals lie perpendicular to the screen, and then after the complete dissolution of amorphous domain, they lie parallel to the screen, and we obtain these nanoplatelets, which dimension are reported here in the case of waxy maize starch. You can see that the lengths range between 40 to 60 nanometer. The width is between 15 to 30 nanometer, and the thickness is around 6 nanometers. So the duration, so the difference in aspect, so we don't obtain any nanorods in this case, is just because starch is not a structural element in nature. So for a structural element, it's necessary to have no rods or fibers. So one of my PhD students tried to optimize the treatment using a response surface methodology, just because the first report on this kind of material, so the treatment was applied, the hydrolysis treatment was applied for 40 days, and the yield was 0.5%. So it's quite low. She tried to optimize, and she reached this objective. So 5 days hydrolysis, and the yield was 15%, which is not so high, but just because of the duration of the treatment and the low temperature. So the reason for this is that during the acid hydrolysis treatment, the starch nanocrystals appear during the first hours of the acid hydrolysis treatment. You can see here from day 1 to day 5, there is coexistence of starch granules or residual granules and starch nanocrystals. So it means that at any time, both micro and nanoscale particles coexist. And of course, the nanocrystals that were formed during the first day disappear during the treatment, for 5 days. So we think about a separation process to increase the final yield, and we tried different options. Differential centrifugation, so it was not very successful. cross-flow ceramic membrane microfiltration, and enzymatic pretreatment. I will show you just this enzymatic pretreatment. You can see here the starch granules that were enzymatically hydrolyzed with different doses of enzyme. And you can see that this treatment creates some holes at the surface of the granules that should facilitate the penetration of acid during the treatment. So this is the same starch granules, but with different enzyme. And after this pre-treatment for 2 hours, we submit the material to an acid hydrolysis treatment, and you can see the extent of hydrolysis as a function of time. So this is the acid hydrolysis treatment without any pre-treatment, and this is with pre-treatment, and you can see that we can reduce the duration of the acid hydrolysis treatment because of these holes that facilitate the penetration of acid. So this is the same here. I forgot to remove it. So now I come back to the possible applications of this nanomaterial. So mainly cellulose nanomaterials because they are commercially available. So different applications can be found, like for example, in coatings, adhesives, energy, ink and printing, pulp and paper, composites, electronics, filtration, textile, construction, packaging, food industry, cosmetics, emulsion, biomedicals, or in the form of films. And these new applications, or for some of them, new application for cellulose, results from the decrease in the size of the material from the micro to the nanoscale. And so I will try to show you what are the difference between these two scales. So, of course, when decreasing the size of the particle, the specific surface area increases. So it moves from about 1 square meter per gram for cellulose fiber to few hundred square meter per gram. So you can see here, for example, the evolution of the specific surface area as a function of the diameter of cellulosic nanorods. And you can see that below 20 nanometer, which is the range of cellulose nanocrystals, there is a huge increase in the specific surface area. And this increased specific surface area results in the viscosity of cellulose nanomaterial in suspension, because of course, when increasing the specific surface area, more water molecules are in contact with the nanoparticles, meaning that they are immobilized at the surface. You can see here also the evolution of the storage shear modulus, so the viscosity of the suspension as a function of the concentration. And you can see that with only few percent, there is a huge increase in the viscosity of the suspension. This is because we obtain this gel. And we can think about possible application in food industry, cosmetic, or pharmaceutical industries. So also because of this high specific surface area, it's possible to submit the suspension to a freeze-drying treatment in order to remove water, avoiding the collapse of the microfibrils, and we can produce lightweight and highly porous foams and aerogel or cryogel. You have some examples here of this aerogel. So depending on the liquid medium, so it can be, of course, water, or it can be a mixture of acetone and water, the porosity can be controlled. And you can see that very low densities can be obtained for these aerogels, meaning that we can apply this nanocellulosic material for porous templates or filtration. Also, it's possible to fix or to attach some particles at the surface of these nanofibrils or microfibrils. You have one example here in which magnetic aerogel have been produced using cobalt ferrite nanoparticles, different contents, which are attached on the surface of the nanofibrils. with possible applications for microfluidic devices and electronic actuators. Another change also when changing the size of the particle is the aspect ratio. So the aspect ratio is the ratio between the length to the diameter of the rod-like nanoparticles. So it ranges between 10 to about 100 for cellulose nanocrystals. It is much higher for cellulose nanofibrils, but it is difficult to determine. You have some examples here of cellulose nanocrystals prepared from cotton, and so the aspect ratio is quite low, it's around 10. Tunicate is this sea animal, and the cellulose which is extracted from this animal is called tunicide. And you can see that in this case, the aspect ratio is much higher, around 70. The same thing here for capim dorado. I don't know if you know capim dorado, so it's quite a specific source of cellulose. It comes from Tocantins, which is a region of Amazonia. It is used for jewelry and other purposes. In fact, I had a Brazilian PhD student that brings some fibers and we prepare nanocrystals. And you can see that, again, the aspect ratio is quite high. And this is another example of cellulose nanocrystals with an aspect ratio close to 100 for nanorods or nanocrystals extracted from soy hulls. This is important for composite applications because in composite science, it's necessary to have fibers with a high aspect ratio. This is just because it optimizes the tensile stress in the fiber, meaning that we can fully profit of the strength of the fibers. Also, the average distance between the particle decreases as their size decreases. So it means that we can expect some interactions between the nanoparticles. Also, it's well known that nanoparticles are weight efficient, meaning that we can improve the properties for low filler content without detrimental effect on impact resistance and plastic deformation. So usually in composite science, for example, when using carbon or glass fibers, it's necessary to use at least 25 to 30% fibers to have an improvement in the mechanical properties. So it means that, of course, there is less matrix material and the ductility or the elongation at break of the material decreases. When using nanoparticles, we have a significant improvement in the mechanical properties with less than 5%, meaning that we keep the ductility of the material, meaning that we have a more or stiffer material, but with a good elongation at break. So reduction of gas diffusion or barrier effect. In fact, these nanoparticles can be dispersed in a polymeric matrix, and it creates a tortuous path for gas molecules, meaning that the diffusion is more difficult. Or these nanoparticles, nanocellulose, for example, can be used as a coating on, for example, paperboard to improve the barrier properties. So the problem is that, of course, cellulose is hydrophilic, and it's possible to protect this coating with a polymer, for example, polylactic acid in this case. And of course, we can think about possible applications in the packaging field. So this is an example in which nanocellulose composites have been prepared with bismuth complex content that can inhibit the growth of bacteria and fungi. You have here the zone of inhibition during the bacterial growth as a function of the percentage of bismuth loading, and you can see that there is, yes, thank you. You can see that there is an increase in the, or a decrease in the growth of bacteria and fungi. And of course, we can think also about the preparation of active packaging. So sorry. So small particles are invisible. not really invisible, but of course, if the size is lower than the wavelength of visible light, we cannot see these particles. So it means that it's possible to prepare transparent coatings or transparent films. You have few examples here. So here, this is the transparency of the film. It was made from only cellulose nanofibrils. You can see here the freeze-dry material, and so remember that this material is porous, and because of this porosity, the film is opaque. So it's possible to remove this porosity by pressing the film, and in this case, we obtain this translucent film. To increase the transparency of the film, it's necessary to remove the surface roughness. And this can be done by a polishing treatment. And you can see that we obtain a transparent film that is composed of only cellulose. So it means that it's a transparent paper or nano paper in this case. Also, when using an amorphous or transparent polymeric matrix, usually when adding chitin or, sorry, not chitin, glass or cellulose fibers, the transparency is lost because of the size of the fibers. When adding, in this case, for example, 60% bacterial cellulose nanofibers to an acrylic resin, you can see that we keep the transparency of the film. And so this is another example with only 5%. So the transparency of the film of the polymer is maintained, but of course the mechanical properties are improved. So also regarding the optical properties, there is another interesting property which is observed only for nanorods, for chitin or cellulose nanocrystals. In fact, depending on the concentration of the nanorods, we can have an isotropic phase if the concentration is low, so meaning that there is a random orientation of the nanorods, but by increasing the concentration of the dispersion, we have a self-alignment of the nanorods. And we obtain what is called a chiral nematic structure. And you can see that in this case, we have an alignment of the nanorods in a given plane. And when considering the successive plane, we have a change in the orientation of these nanorods. And this can be observed by looking to the dispersion, to the suspension, using polarized light. We obtain these colored domains, which is called birefringence of the suspension. So this is explained here. And by evaporating water, it's possible to keep this arrangement of this alignment of the nanorods, and we can obtain films, nanocellulosic films, with colors that change depending on the angle of observation, which is called iridescence, that can be found in nature, in some butterfly, like morpho, or on the shell of beetles, and so on. So in this case, it's not cellulose nanofibers, but it's collagen nanofibers. So what is interesting is that the wavelengths of the reflect color, so it's given by this equation, in which P is the pitch of the arrangement. So the pitch corresponds to this distance for which we can recover the same orientation of the nanorods. And so this pitch can be controlled through the ionic strength, for example, by adding different electrolytes. Here you can see that the pitch decreases just because there is less repulsion between the nanorods. It can be controlled also through the temperature, the concentration, the exposure to magnetic field, or ultrasonic treatment. You have one example here of films made from cellulose nanocrystals, but the suspension was submitted to ultrasonic treatment with different strengths, and we can tune the color. And of course, we can think about possible application for security papers, UV or IR reflective barrier. So remember that cellulose also chitin, are structural elements. So they provide the mechanical properties to plants, for example. And of course, this is interesting at the nanoscale. Because when decreasing the size of the fiber by removing the transparent domains, we remove the defects from the fiber, meaning that the stiffness of the material should increase. You have here the tensile modulus. So for different publications, it was obtained experimentally, or it can be obtained by calculation. Of course, you can see that there is a broad range of values because it's quite difficult to determine the stiffness of this nano object. But when looking to the average value, so it's around 130 gigapascal. I don't know if you have an idea about the modulus of glass fibers. So it's around 70 gigapascal. So it means that it's much higher. And of course, in the case of cellulose nanofibrils, so nanomaterials obtained by a mechanical treatment, it's slightly lower because of the presence of amorphous domains. So this is an interesting study. It was reported almost 10 years ago. They use atomistic simulation to predict the fracture energy of 1-beta cellulose nanocrystals. And so the result was the establishment of the ideal dimension that optimizes the fracture energy. And so the nanocrystal should have this dimension. And this is exactly what is found in wood, meaning that nature has already optimized the mechanical strength of cellulose nanocrystals or cellulose crystalline domains. So it was found a long time ago. You can see it almost 30 years ago. So it was my first paper on cellulose nanocrystals. So we tried to use these nanoparticles for composite application. So we mix these nanoparticles with a polymeric matrix. First, it was a copolymer of styrene and butyl acrylate. And it was quite easy because this material is available in the form of a latex, an aqueous dispersion of polymer. So it means that we just have to mix the two aqueous dispersion, evaporate water, and then we can determine the mechanical properties of the film. And you can see here the evolution of the storage shear modulus above the glass transition temperature of the material as a function of the cellulose nanocrystal content. In blue, the experimental data. And in material science, it's usual to compare this experimental data to data which are predicted using different models, assuming a given morphology to the material. I mean by morphology, the arrangement of the two phases. And so we use these two models, Alpine-Cardoz and percolation approach. So Alpine-Cardoz take into account the stiffness of the nanorods, but in this model, there is no interaction between the nanoparticle. And you can see that the model failed to predict the experimental data. And when using this percolation approach that take into account the interactions between the nanoparticles, you can see that we have a good agreement with the experimental data. So what is the meaning of this? It means that we have a mechanical percolation effect in this nanocomposite. So not only the stiffness of the nanomaterial or the nanorods is important, but also the interactions between these nanoparticles. So it allows explaining the high reinforcing effect that was observed. So it's like for a paper sheet, the strength or the stiffness of the paper sheet is due to strong interaction between the fiber through hydrogen bonding. And also we observe a thermal stabilization of the composite. And this is because water evaporation is a slow process. When using other processing techniques, we don't observe this thermal stabilization. So cellulose is also a lightweight materials. Cellulose nanomaterial modulus is potentially stronger than steel and similar to Kevlar. You have in this table different materials glass, Kevlar, steel, microfibrillate cellulose or cellulose nanofiber or nanofibrils, cellulose nanocrystals. So we have seen that the modulus is around 100 or 130 gigapascal. You have here the density of the material, and the specific modulus is obtained by dividing the modulus by the density of the material. And you can see that in the case of cellulose nanomaterial, it is much higher than for steel or for glass, and in the same range as Kevlar. And of course, we can think about composite application because we have both strong and lightweight material. Thermal properties. So when preparing a film from cellulose nanofibrils or cellulose nanocrystal or from chitin also, it is observed that the thermal expansion coefficient is very low. And this is due to the high crystallinity of the constitutive nanorods, but also to the strength of the cellulose nanomaterial network interactions. And of course, it can be used to reduce the thermal expansion coefficient of polymer nanocomposite if the connection is sufficiently high. So amphiphilic properties, in fact, these nanorods, cellulose nanorods, have some OH-rich surface, which are, of course, polar, and CH-rich surface, which are non-polar, meaning that we have a kind of surfactant that can be used to prepare Pickering emulsion. So you know that to prepare an oil in water emulsion, usually surfactant molecules are used, but also solid particles can be used. In the case, it consists of Pickering emulsion. And so, of course, it can be used. And you have an example here. You have a styrene Pickering emulsion stabilized by CNC. So styrene is in red and in black it's water. And you can see that the nanorods or nanocrystals locate at the surface of the droplet, oil droplet. We can see here and more here that the nanocrystals are located at the surface and act as a stabilizer for the emulsion. I think one slide is missing. Remove it probably. It was just to say that, of course, on the surface of cellulose nanomaterials, there is a high density of OH groups, hydroxyl groups, meaning that it's easy to change or to modify these OH groups using small molecules or longer molecules, macromolecules, just to tune the hydrophilicity or hydrophobicity of these materials depending on the application. So directly the conclusion. So there is a growing interest in the non-food usage of renewable resources, but also in nanotechnology. And polysaccharides are interesting candidates for this because they are low-cost material, they are abundant. We can use agricultural byproduct to produce this nanomaterial. These materials are renewable. It's possible to prepare nanoparticles or nanomaterials with different morphologies and aspect ratio. So it can be long filaments, nanorods, nanoplatelets in the case of starch. And of course, there are new properties for these nano-sized particles, mechanical properties, decreased permeability to gases and water, increased thermal stability at distortion temperature. So the main issue for the most abundant use of this nanomaterial is, of course, the price of the material, and it's necessary to optimize the preparation of this nanoparticle, but also the processing of nanocomposites. We discussed yesterday about extrusion. Of course, it's more convenient than water evaporation. So thank you for your attention, and thank you to EcoSud. It's because of this project that I am here in Conception. Thank you very much.
Thank you very much, Dr. Dufresne, for your nice talk. We have time for some questions, if anybody has some. Well, if nobody, I can, well, okay.
Thank you very much. Thank you very much for your talk. Since I was working in the pretreatment of biomass to separate the three main components and use mostly dilute sulfuric acid or some formic. Yeah, we use diluted acid. Yeah, for mine, yes. So when you reduce actually to hydrolyze the starch, and you reduce the for per day, it's almost a month, the pretreatment. How was actually the concentration of the acid, and what kind of acid did you use?
I don't remember.
Oh, okay. Don't
I
worry.
don't remember it in the publication. So the publication was in 2004. No, I don't remember. But we changed different parameters, like for example, the temperature of the acid hydrolysis treatment, the concentration of the acid, the duration of the treatment. But I don't remember.
I can read the paper. Don't worry. Yeah, yeah. It was my question because actually one of the points was when I read about starch is that concentrated acid, low temperature can be good because there is no degradation of the cell,
This is a
the
problem
glucose.
with
Yeah,
starch.
yeah. But reducing that much of time is a very winning experiment. So I was curious about it. Thank you very much.
Okay. Thank you very much for the talk. Professor Dufresne was very interesting. I have a doubt. Is possible from the synthesis methodology to preferentially expose the non-polar or polar phase from the material? And how can we do that? How
Yes,
can we
I
do that?
didn't do it, but I was a member of PhD thesis defense in Montreal a few years ago, and sorry, I have to remember. I don't know, but it tried to manage the orientation of the nanocrystals in the suspension. I don't remember the way that was followed, but I'm sorry. It's it's Charles Bruel. Maybe if you can try to find the papers. So I don't remember anything.
Sorry. Anybody? Yeah.
Hello, many thanks for your presentation. And I have a question about when you talk about the crystallinity index that increase when the thermal stability were low.
No. In fact, I mentioned that the crystallinity increases, and this is a sign of the defibrillation process. This is just because during the mechanical treatment, of course, the amorphous domains are less stiff. So it means that they can be removed during the treatment. And for the
but the crystallinity index is related with the thermal stability of the nanomaterial?
No, the thermal stability of cellulose is quite low. It's maybe 200 or 200 degrees Celsius. And it is even lower for cellulose nanocrystals when they are prepared by an acid hydrolysis treatment with sulfuric acid. Because of sulfate groups.
And also in the first slide, you say that after hydrolysis process, acid hydrolysis process, you can desulfurate the nanocrystal. How is
with
this?
NaOH solution? This is one option to improve the thermal stability. There are some other. It's possible also to coat the nanocrystals, for example, with ammonium salt, just to protect, in fact, the sulfate groups. And the result is an increase in the thermal stability of the nanocrystals.
Great, thank you.
Any more questions?
So it's one.
Congratulations of the presentation. It's
you.
definitely good material, but I wonder why we have not seen in industry.
This is a big question. In fact, for example, cellulose nanocrystals, so it's not the case for chitin, it's not the case for starch, but cellulose nanofibrils or nanocrystals are produced and commercialized since more than 10 years.
Oh.
But the problem is that, of course, so it's mainly pulp and paper industry that face some problems, that want to find new markets. So it means that it's mainly in North Europe, Scandinavia, and in North America. The problem is that they are producing this material that don't know exactly what can be the application. And of course, depending on the application, the price can change. Because if it is for use in pulp and paper industry, the price should be lower than if the application is in cosmetics, for example. And the problem is that many industries, I think, are interested by this material because they are looking for materials with good properties, which are renewable and biodegradable and so on. So they are interested by these materials, but of course, it depends on the price. And so it means that we don't know exactly. So this is for cellulose, but I think that for chitin, it will maybe start soon, because I have been contacted by a company in China about 1 year ago, and we had a Zoom meeting. And so it's a company which is producing chitin, and they plan to produce chitin nanocrystals. And they asked me if I was ready to go to China. No.
Thanks.
Any more questions? I have a question for you about the reinforcement with nanocrystals. You mentioned that an important part of the reinforcement is the particle-particle interaction, right?
Exactly.
So,
Because the Alpine Cardos model take into account not only the stiffness of the nanoparticle.
Yes.
And so the reinforcement is very
I am wondering, do you mean nano-crystal interaction?
Yes.
Yeah. How can they, I am just curious, how can they interact when you're using like 0.2% or whatever, like very low concentration?
0.2%, it's okay, but it depends on the aspect ratio of the nanoparticle. For example, in the case of tunicate nanocrystals that we use in the study I showed, the first study, the aspect ratio is around 70. Okay, and for this aspect ratio, we have what is called a percolation effect or interaction between the nanoparticles from 1% by volume.
All right.
Of course, if the aspect ratio is lower, for example, in the case of cotton, the percolation threshold or the content of nanocrystals necessary to form this network is higher. I don't remember, it's maybe 7% or something like that.
Yeah, I understand. And that leads me to another question. Does that mean that they have to interact somehow like through hydrogen bonding?
Yes, yeah, sorry,
right.
I didn't mention. Yes, it's hydrogen bonding.
That's
so that's strong interaction.
Yes, because it's interesting because as you know, when you try to compatibilize, and actually you mentioned, many researchers are trying to functionalize the surface, right? So you want to make it less polar so you can compatibilize somehow, but that goes against what you are talking here.
There
so
are
that's
effects.
Yeah.
You improve the dispersion, which is of course important, but you avoid the interaction between them.
So you have to be somehow in between.
Yes.
All right.
I tried something a few years ago with a Chinese PhD student. You know that we can functionalize only the end of the nanocrystals. And so we try to functionalize this end and to keep, in fact, the OH group on the surface. And we try to disperse this in natural rubber.
All right.
And so it was not really successful, but so we just hope to have good interaction because of this end modification.
I understand completely,
But interaction between the nanoparticles.
Very interesting. Yeah, thank you very much. Anybody else? Any other questions? All right. If not, please, let's give an applause to Dr. Dufresne.
Thank you.
They can take care. No
Okay.
worries. No worries. Just keep. Yeah, we'll keep that. Okay. So I will just give this back, and then we can come back to the department. Right?
Okay.
Yeah. Permiso. Gracias.